Welcome, everybody. So this talk is going to be about where the Java language is going, and you'll notice the subtitle, late 2019 edition. I've adopted the Apple, version numbering scheme because this is a topic that is a moving target. We're delivering rapidly, we're innovating rapidly. So what I might speak about in a talk with the same title earlier in the year might not be the same content later in the year. So this is to prove that I work at Oracle. So you've all seen that. Now you believe me. OK, so Java has been around for a long time, almost 25 years. And it seems to be a hobby to periodically declare Java to be dead. And if it's a popular hobby, I can understand that. But my job is to confound those beliefs. And so 20, 25 years later, Java is still the world's most popular programming platform by some measures. And we want that to continue to be the case for a long time going forward. And our super, super secret plan for doing that is to stay relevant. OK, big secret. Stay relevant to the problems people want to solve. Stay relevant to the hardware people want to run on. Keep the promises we made to our users by having code that they wrote 5, 10, 15, 20 years ago still work, so that we don't invalidate the investment people have made in their code. So we talk about this in terms of keeping our promises. We've made these implicit promises that Java will remain largely the same Java, even though it evolves. And that means code you wrote 20 years ago should just continue to work. And we think that this is really the secret to Java's success, is that the investment people have made in writing Java code, in learning how to program in Java, is not an investment that depreciates rapidly, because things you did, things you learned 5, 10, 15, 20 years ago are still useful. And this has a cost. Evolving with compatibility has a cost. It means things happen more slowly than they might otherwise happen if we were willing to move fast and break things. A good example of that is how did we do generics, right? Generics were originally scheduled for Java 1.3, then 1.4, and then 5. And it was a long time coming. And the reason it was a long time coming is that we were trying to figure out how to do it in a migration-compatible way, so that existing code would still run after, say, a library was generified, and that code would have the choice to migrate gradually. It could migrate immediately, later, or never, as it saw fit, and have there be graceful degradation at the boundaries with no flag days. This is like 80% of the work, and this is why evolving Java takes longer than evolving other languages, because we're trying not to invalidate your investment in existing code. And if we do this right, we get a sort of nice bonus, like we did with lambdas. So Java made the choice to do lambdas using nominal function types, functional interfaces, instead of structural function types. And a lot of people looked at that and said, you guys are crazy. The obvious way to do it is to put structural function types in the language. And that would have been a reasonable way to do it if we were starting from a clean sheet of paper. But one of the reasons we did it this way is it meant that we weren't disrupting the way Java developers think about APIs. And in fact, 20-year-old APIs that had no idea lambdas were coming in 20 years could work with lambdas on day one without recompilation, because they worked with abstractions like runnable and comparator and things like that. So the compatibility is very important to us, especially migration compatibility. It has a cost, but it has a big benefit. Another reason, I'm getting through all the reasons why Java moves slowly. We'll get them out of the way first, and then we'll talk about the things that Java is doing. Another reason why you might perceive Java to move slowly is we're very aware that we're working on a long time scale, and language features are forever. Any language feature we put in the language today is going to be there for a long time. We're going to have to support it for a long time. And it's going to be interacting with every other feature that's in the language, past, present, and future. And so the cost of making a mistake means not only do we get it wrong and can't fix it, but it might be also that there's 10 other good things we can't do because it interacts badly with something that we've already done. And so the motivation there is, if you don't know what the right thing to do is, then the right thing is do nothing and wait until you do know what the right thing to do is. And I'll posit that generics were a prime example of that. I mean, it's not like we didn't know what parametric polymorphism was in 1995, and it's not that we didn't think it was important. We didn't know how to do it right. And if someone had said, Java 1.0 must have generics, well, we could have met that requirement, and we probably would have gotten something like C++ templates And how happy would we all be about that? So instead, we had to wait 10 years. That was awful. But we got a generic type system that made much more sense for Java than what we would have gotten in 1995. And as programmers, we obsess about language features because we look at code all day. But language features are a means to an end, and that end is making it easier to build and maintain reliable programs. That's really what it's about. Okay, so I keep talking about this in the context of evolution because I really think that that's what's going on. This is an ecosystem, and in that ecosystem, you can think of programming languages as being the predators and programming problems as being the food supply. And there's an environment that we all work in, computing hardware and the state of practices and fashions and all that. And in a real ecosystem, things change. And if the participants of that ecosystem don't evolve, they die out. And so programming tools that might have been ideal for solving the programming problems of one era may not be ideal for solving the programming problems of another era. And if they don't evolve, then they'll be replaced by something else. So we want to remain relevant. We want people to keep programming in Java. So we need to evolve Java to keep up with expectations, hardware, what people intend to do with their programming languages, and maybe even to some degree developer fashion. So we're clearly not done. We're never going to be done. We're going to continue to evolve. But we want to do it carefully so that we don't get ourselves into a situation where you can't cram anything else into this language. We've all seen languages that have suffered that fate. We're still waiting for Perl 6, right? Because Perl got full, and they couldn't figure out how to evolve it. OK, so going over this very quickly because you heard about this at the keynote. About 2 years ago, we switched to a 6-month rapid release cadence. We've delivered 4 releases under that cadence. As compared to the old way of doing things, which were these 2 to 4 years, you hope it's 2, in reality it's closer to 4, feature-driven releases. And we're all familiar with what was wrong with the old model. It took a long time. It was difficult to accurately plan. The cost of missing the train was enormous. That meant we had a huge overhead of release management. Little features got stuck behind big ones. And the world has changed. Expectations have changed, and by moving faster, not only can we deliver value faster, but we can also let go of some of that crushing release management overhead and spend more of our energy on developing features. Java 9 was the last release under the old model, and since then, every 6 months, we've delivered a release. Java 10, 11, 12, 13 just went live today, and we're halfway through the development cycle for 14. And it's working great. It's really working great. And there's, as I said yesterday, there's useful features in every version. Not necessarily features from every category. There's not necessarily language features in every version. There might be runtime features or library features. And it kind of changes the way we have to look at the contents of a release, because we used to look at what's the big thing and then decide whether that was important to us. Now, there aren't going to be big things, because the big things are going to be broken down into smaller things, and we kind of have to look at the totality of, well, what are all the improvements we've seen in the last 6 months, a year, 2 years, et cetera. It's a little bit of a different way of looking at it, but I think it's a healthier way of looking at it. And language features, because they are special in the sense that they're almost impossible to change, unlike library features, which can be extended or deprecated, we're sort of taking an extra effort to get them right by having a mechanism which we call preview features. So a preview feature is a fully complete feature. It has a full implementation and specification. But it is sort of in provisional status for 6 to 12 months while we gather feedback. So in the event that we messed up, there is an opportunity for people to say, whoa, you didn't think about this particular case. And we can look at that feedback and act on it and decide whether we want to revise it based on feedback. And we think this is a positive thing. Might be a little bit frustrating that there's a feature that's like 99.9% done, but you can't use it in production yet. This is the cost of not making a mistake. And so we expect that all language features will go through at least one round of preview. So the best kind of feedback, the kind of feedback that we really hope to get from people, is telling us things that we didn't know, right? There's lots of people have opinions about what the syntax should be. We've heard all of those. And that's not necessarily particularly actionable feedback, because if different people have different opinions, you can't make them all happy. But telling us things that we didn't know, of the form, I tried it this way, and look at this strange behavior I got. That's the kind of feedback that we might actually act on and change a feature before it goes permanent. So to use preview features, you have to enable them explicitly so that, and the reason for this is what you don't want is someone using preview features in a library that they put in Maven Central, that's one of your indirect dependencies, and all of a sudden you have a dependency on a specific version of Java that you didn't realize you did. And so you have to be a little bit explicit to enable them at compile and runtime. And IntelliJ IDE has IDE support for preview features that if you go to the language level picker, and it'll say, you'll see 11, 12, 12 with preview. And it will it will adjust its view of the language depending on what you've selected. So we think this is a successful mechanism. It's the jury's still out. If it doesn't work, we will try something else. Okay, so let's actually talk about the language instead of meta language issues. In OpenJDK, we have a number of projects that have funny names, and they have rough categorizations. And Project Amber is the umbrella project for what we call right-sizing language ceremony. It's the smaller language features that that are aimed at developer productivity. They're not the big earth-shaking, change the platform kind of features like Valhalla is, but they're the features that a lot of developers care about. And Project Amber has already delivered local variable type inference in 10, switch expressions in 12, text blocks in 13, and there's a pretty rich pipeline of stuff that's coming. So even though 10 is old news, that's 3 releases ago, I suspect that some of you aren't on 10 yet. Who's not on 10 yet? You should all be ashamed. So it's new to you, so I can talk about it in my futures talk, even though it's way in the past for me. So you're all familiar with the fact that in order to declare a variable in Java, you have to give it an explicit type, and then you have the variable name, and then maybe you have an initializer. And sometimes this is helpful. Sometimes it makes it easier to tell what's going on. Sometimes it just gets in the way because the type name is redundant with the variable name or is obvious from the context, or the type name is this big, god-awful, abstract broker, provider, factory, locator system, and you just don't want to have to say that. And so what is local variable type inference about? It's about allowing you to request that the compiler infer the type of a local variable for you, strictly on the basis of what's the type of the initializer on the right-hand side. So Java has had type inference since Java 5. We had type inference for generic type variables. In 7, we added type inference for constructor type variables. In 8, we added inference for lambda formals. And so this is just another place that we're using type inference where you can be explicit or not be explicit. In some cases, writing it this way will make your code more readable because the most important thing in most lines of this form is the variable name. That's the place where the programmer actually used intelligence and creativity to say what they meant. And so that's kind of the thing that you'd like to be front and center in the reader's perspective. If it turns out that deleting the type it merely obfuscates what's going on, feel free to use an explicit type. This isn't a requirement to leave the types out. It's an option. And in a lot of cases, the program becomes more readable, or at least as readable as it was in the beginning, as long as you pick reasonable variable names, which we all do all the time, right? Right. So if you're interested in this topic, you can leave the room and go 2 rooms over and go to Stuart Marks's talk, who's doing a whole talk on this one slide. He's obviously getting into a lot more detail than I will. But I see you've chosen to stay here, so let's go forward. What are the rules? OK, this is only for local variables. It's not for method return types or fields for reasons that I think should be obvious. A lot of people describe this as being syntactic sugar. That's actually an incorrect use of the term syntactic sugar. It's not syntactic at all. It's about type analysis. And the Java type system is a little more complicated than a lot of people give it credit for. So I'll show you a few examples of cases where the type of something isn't quite the type you think. So for example, supposing I have an instance of something called this class. So I say this.getClass. And what's the type of that? You might think it's class of question mark, but it's actually class of some capture type. Capture types are part of the Java type system. They have been since Java 5. Most of the time, they stay where we can't see them, which is how we like it. But they do, if you ask the compiler what's the type of the thing on the right-hand side, it will tell you accurately, and you may get a type that surprises you. Here's another example. List out of 1, 2, 3. Okay, you might think that the result would just be a list of question, or a list of question extends object, or something like that. But actually, integer and string have more in common than you think. They're both serializable, they're both comparable. So you're going to get a list of question extends, serializable, and comparable, where there's something in the type argument for comparable, which is actually question extends, serializable, and comparable, ... And so these types, so here we see a capture type, here we see an intersection type. These are types that are part of the type system. A lot of developers don't know about them. So this is a feature that is going to expose some of the dark corners of the type system to users where they might see them for the first time. And that's one of the trade-offs we make about allowing you to say, I'm going to let the compiler do this for me. The compiler might do it a little differently than you would have yourself. Sort of a funny meta issue about this feature is, so this was like the most commonly requested feature of like people who would stop me in the hallway as I walk in conferences and come up to me and say, I really want var. They may not know it's called local variable type inference, but they say, I really want var. Why can't I have var? Scala has var, Kotlin has var. And okay, after several years of hearing that over and over again, and being able now to work on smaller features instead of big features and big releases, we said, all right, maybe it is time for Java to adopt that. So we said, okay, we're going to do that. You guys happy? No, of course people weren't happy. Immediately, the other half of the community, who hadn't been saying anything, came out of the woodwork saying, oh, you're just giving into fashion. Oh, you're encouraging bad developers to write bad code. Like they need encouragement, right? And in the end, neither of these groups turned out to be right. By the time we actually shipped it, no one had anything to say about it. They had all moved on, right? So, it's a little bit of a cautionary tale to not take quite so seriously everybody's rantings about what will or won't happen if you do or don't make a certain change in the language. In reality, it's a language feature that enables us to maybe write better code, maybe write worse code, and as long as we're able to use our judgment, you all have that, right? Then it'll be fine. And Stuart wrote a lovely style guide and FAQ about the feature. They're up on the OpenJDK website about what's this feature for, why did we do it, when would be good places to use it, when would be bad places to use it, what would be things I should think about when considering using it, which I think are, should be helpful in using this feature effectively. Okay, so let's move on to what we did in Java 12, switch expressions. A lot of switch, so switch can only be a statement currently, not an expression. And that's a little unfortunate because it turns out if you look at real-world switch statements, most of them are actually simulating expressions in a somewhat roundabout way. And switch, everyone loves to beat up on switch. It was probably one of the weaker features in Java 1.0, in part because I think it was copied a little too literally from C. And so, for example, the default is to fall through rather than not to fall through. So if you want to not fall through, you have to say break, which you have to say 99.9% of the time. And so we had already been looking at enhancements to switch as part of pattern matching, which I'll talk about in a bit, and switch expressions sort of dropped out naturally. So here's an example of a switch where we're simulating an expression. We're doing some multi-way conditional, and in each arm we're going to stuff some value in a local variable, and then we're going to go on and use it. And there's a lot of verbosity here. There's a number of places to make mistakes. If you forget to break, then you have a subtle bug. And then to add insult to injury, even though we're switching over an enum and we've covered all the days of the enum, we still have to have a default clause that says, I don't know what happened. And so, it's not surprising why people, like to hate on switch. And so we have this redundancy, and we have the redundancy of the breaks, and then we have that. Here, I've rewritten it as a switch expression. It's gotten a lot more compact, that's nice, but more importantly, it's gotten less error prone because as an expression, you expect to see exactly one expression on the right side of that arrow, so I don't have to say break. And because I'm switching over an enum and the compiler has validated that I've covered all the cases of the enum, I don't need a default. The compiler does generate a default clause for me in the event that somebody adds a day to the week between compilation and runtime. But in general, this is a lot closer to the code that we probably had in mind when we sat down to write this. So that went into 12 as a preview feature. We made some small modifications to it, and it re-previewed in 13, and we fully expect that it will be a permanent feature in 14. This is actually two separate enhancements to switch that are orthogonal. One is switch can now be either a statement or an expression, and the other is the new form of switch labels where previously it was case something colon and then some statements, and the other form is case label arrow and then a single consequence. And in fact, you can mix and match these two things. And so you can use either form of label with either switch as an expression or statement. I expect most of the time people will choose the expression arrow quadrant of this 2x2 matrix. But we did it this way because we felt that by defining it as two simpler features that interacted nicely, it was simpler than having switch statements work this way and switch expressions work a totally different way. And so people call them switch expressions even though the feature is a little bit more complicated than that. In JDK 13, we did another feature that was kind of in the same category of things that people bug me in the hallways about, which is multi-line strings. This is another persistent pain point of I have some snippet of HTML or SQL or JSON that I want to have embedded in my Java source code, and it's more than one line, so I have to represent it as a concatenation, a bunch of strings with some \ns manually inserted, which is error prone and obfuscatory. It makes it harder to read and easier to make a mistake. So wouldn't it be nice to be able to say what I mean? And it's not a particularly sophisticated feature, but that's okay. And so this is how we have to do it today. And so the yellow stuff is the stuff we would like to get rid of. And if I express this as a text block, it looks something like this, which is to say it's a string literal. It looks a lot like the old kind of string literals. You can use all the same escape sequences inside of it. It has a different delimiter, and it's allowed to span multiple lines. That's the difference. And this is easier to read. It's also easier to write. You can just cut and paste your HTML code directly in. And switching from a single line format to a multi-line format brings up the question of, what about this stuff? I indented my code because I wanted it to be pretty and readable, and that's a good thing. On the other hand, now there's a bunch of extra spaces in between my delimiters. Are those part of my string or not? There was a lot of debate when we were designing this feature about how to do that. And we eventually settled on a heuristic that allows the compiler to decide which space is incidental, in other words, which has been inserted purely for the purpose of aligning the text literal with the code, and which space is essential. And so the spaces corresponding to the dots would not actually appear in the output of the string. And you're probably thinking about 17 different what about cases in the back of your head. And yes, those are all valid, and yes, within the rules of the heuristics that we've defined, they can all be expressed by changing the positions of the delimiters. And this was an interesting feature to design because we looked at what other languages do. And very often, when you look at what other languages do in a particular area, you see 2 or 3 clusters of, well, these 6 languages do this thing this way, and these 4 languages have chosen this other way. We looked at multi-line and raw strings in 15 languages and found 15 different ways to do it. So, of course, what did we do? You got it. For good reasons, but it was very clear that subjectiveness was an essential part of the design process for all of the feature in every language, where the designer clearly had an intended use case in mind and optimized the feature for that case. And that's allowed. There isn't, I mean, if we saw 15 other languages all did it the same way, that would be reasonable evidence that there might be a reason to do it that way. When you see everybody's done it a different way, that's kind of reasonable evidence that there may not be one right answer. And so we chose a answer. Okay, so let's talk about what's coming soon. You've all been through the pain of declaring domain objects, by which is modeling data with classes, and it's well understood how to do this. You read effective Java; it tells you exactly what to do. But oh my God, is it tedious, right? Constructors and accessors and equals and hash code and toString, and this is bad for a couple reasons. One is it's annoying to write, but that's actually not the important reason. It's annoying to read. You have to read a lot of low-value code to validate that you didn't need to read that code. So that's kind of wasting the reader's time. We don't like that. And it's error-prone. It's really easy to make a cut-and-paste error when doing this. And so we felt that it was important to have a way to say a class is just a container for its data. And this is actually a trick. This embodies a trick that we did in Java 5 with enums, where an enum is kind of this deal between the compiler and the programmer, where the programmer says, I'm willing to give up something. I'm willing to give up control over instances. And the compiler can say, OK, well, if you're willing to let me manage the instances, then I can deal with the details of instance creation and equals and construction and all of that for you. So records are a kind of similar deal, where the programmer says, this is just a dumb class. The API should be derived strictly from the data description. And in return, the compiler can fill in the boilerplate because you've told it what to do. Okay? So we'd like to write this. We can't write that. We have to write this. And all of that small type code is, I would call it negative value code. It gets in the way. It has to be read. You can get it wrong. It's a place to make mistakes. And a record is a class. It's not something special and different. It's a class, but it's a class whose representation and API are derived from a common state vector. So in this case, I say a point is an int x and an int y. That means I get representation for x and y. I get private fields, and I get constructor, accessors, equal, hash code, toString. And if I want to refine the implementation of those, that's fine. I just put it between the brackets because it's a class. If I want to add other behavior, that's fine. I put it between the brackets because it's a class. So records, they give us reduction in boilerplate, but they're not about boilerplate. They're about semantics. They're about saying what this class is. It's a carrier for its data. And then we derive the boilerplate reduction from the semantic commitment. And like I said, this is a game we've played before. It's worked out well. I think it will work out nicely for records. And it also connects very nicely with the next two features I'm going to talk about, which are sealed types and pattern matching. So record types are also known as product types in the literature. Their state space is the Cartesian product of a number of other types. And in some languages, like functional languages like ML, product types are sort of one of the primitive abstractions for defining data. The other half of algebraic data types, called sum types, is also useful. A sum is a discriminated union. It's being able to say a shape is a circle or a square, and nothing else. And that allows the compiler to reason about, well, if I did something for circles and I did something for squares, then I've covered all the shapes. Sealed types are expressed as a modifier on a class declaration, where you can say sealed interface or sealed class. And so to represent this little mini hierarchy of shapes, I say, OK, I have a sealed interface called shape, and I'm explicitly going to say that a shape is a circle or a rectangle. Those are the types that are permitted to implement shape. If I didn't say it explicitly and they were all co-declared in one class, the compiler would figure it out for you. But you can be explicit about it. And then I say, well, circle's a record that has a center and a radius, and that's a shape. And rectangle's a record, and it has lower left, upper right bounding points, and that's a shape. And a point is, well, that's also a record. And so I've defined a whole hierarchy here of shape classes, including circle and rectangle, fairly compactly. And the compiler can reason. I don't know why it's doing that. The compiler can reason about what a shape means. OK, so let's move forward. These features work together pretty nicely. There's a lot of places where we might use them. So as an example, imagine you've got a method. You're writing a library that's going to compute minimum or maximum value across an array or a list or a collection or something like that. Now, when we're traversing a data set, it's generally easier to compute the minimum maximum at the same time. But if we try to write that ourselves, we would say, oh, I don't know how to return two things, and I don't want to declare a whole class, oh my God, just to return something. So I'll just write two methods, min and max, and I'll make the user call it twice, right? We've all done this where we've cut corners and written the wrong API because it was too much work to write the right API. So one of the things that records do is they reduce the overhead of declaring a new data abstraction so you can write the correct API, the API that you meant to write, as opposed to the one that was easy to write. Another sort of obvious use case here is what was one of the questions that comes up on Stack Overflow about the streams library all the time, which is, supposing I want to do a stream and I want to sort it according to some derived quantity that's expensive to compute. So I don't want to have it computed in the comparator every time. I want to materialize it somewhere, sort by it, and then throw it away. So what I really need is a tuple to describe the element and the derived quantity I'm sorting by. And then I will take my list of elements, I will map it to that, compute the score for every element, and then sort by that, do whatever else I'm going to do in the stream, and then map away the derived tuple and pick out the answer. And this is, again, one of those things that you could do this yourself, but people avoid doing it because it would feel like too much work. And so again, by reducing the amount of work it is to declare the data abstraction you want, and in this particular case, this abstraction is local to the method implementation. That's a local class. You're able to express it so that it's compact and readable and obvious what's going on, and it doesn't pollute your API with exporting an extraneous type. So there's lots and lots more use cases for records and sealed types. Any kind of tree node or document description, objects that simply carry data between two layers in an API, compound map keys, this is one people get wrong all the time, messages in an actor-based system, any kind of wrappers around a value like in the previous example, it doesn't take long to figure out 100 places where you can use this in your code. Okay, so the last big feature I want to talk about, and this is a fairly big feature, but one that we're going to deliver in phases. Excuse me, sir, if you're going to take a call, could you please take it outside? A feature that we're going to deliver in phases is pattern matching. So pattern matching is, again, a feature that, that you might have seen from functional languages. And it's not particularly a functional feature in the sense that it makes perfect sense in object-oriented languages too. So we all write code like this all the time, which is a combination of three things. Asking a question about some object, conditionally extracting some property if the answer to the question was yes, and then putting the result in a temporary intermediate variable. So in the case of instance of and cast, you say if object is an instance of integer, then the next thing I do is cast it to an integer, and then I do something with that. And there's lots to hate about this example. In particular, I have to repeat integer, which is repetition is an opportunity to get something wrong, right? Like let's say I did this by cutting and pasting from some other bit of code, which of course we would never do. It's very easy with this repetition to ask instance of x and then cast it to y. Who's made that mistake? Right? We've all made that mistake. And the reason we've made that mistake is because the language helped us make that mistake by requiring you to repeat yourself. You might say the language is almost daring you to make that mistake. And the other thing that's kind of dumb about it is, well, what else would you do after asking instance of besides cast? Right? Having to do the cast explicitly is just kind of silly. So the essence of pattern matching is to say, let's fuse these three things into one abstraction. So in this particular case, the test is, are you an integer? The conditional extraction is, cast it to integer, and then we want to bind that to a temporary. Some people say, oh, this is easy, just do flow typing, like my other favorite language did. That would be a dumb choice, so we're not going to do that. Flow typing is one of those clever language hacks that looks clever for about 5 minutes until you realize it's a complete dead end and doesn't help you solve any problem other than the use case you had in mind when it occurred to you. So there's a much better answer that goes much, much deeper, which is pattern matching. And so a pattern fuses this concept of test, conditional extraction, and bind into one thing. So one kind of pattern is a type pattern. Type pattern is the simplest kind of pattern, and it looks a lot like a variable declaration for completely non-accidental reasons. And you can put one of those things on the right side of an instance of. You can say if object instance of integer int value. And what that means is, does it match the pattern integer? Yes. If so, cast it to integer and stick an integer in that variable, which is then only in scope inside the body of those brackets. And so eliminates a lot of boilerplate, yay, but also makes it harder to make a whole category of mistakes. There are lots of other kinds of patterns, and they interact very nicely with each other. So type patterns are the simplest. The first phase will just be type patterns an instance of, which will have the beneficial effect of like basically all the casts in the world disappearing, which is like, that's already worth the price of admission. But it's actually a very rich feature. The rabbit hole goes pretty deep, and I'm not even going to plumb halfway down the rabbit hole, but I will talk about what some of the next things we can do with it. Another useful thing of being able to do this is, if you look at the code for a typical equals statement that was generated by your IDE, the control flow is impossible to read. It's if this, then return false. Otherwise this, then return true. Otherwise do this other thing. And you know, that means it takes time to look through it and say, does it do what I think it does? If I express this as a pattern, what I can do is I can bind my instance of and my extraction in one thing, and then continue to use that temporary t in the remainder of the expression. So if the other thing is instance of this class, and its size is equal to my size, and its name is equal to my name, this is a much more straightforward way to express equals. And there are other places we can use pattern matching as well. Right now, when we want to do complex multi-way, like are you an X, are you a Y, are you a Z, we have these chains of instance of and cast, which are like repetition city, right? We have the same repetition we had before, and then we have the repetition of asking the question over and over again, and we have the repetition of doing the, assigning to a temporary over and over again, with all of the attendant ways to make mistakes. And what we can do is say, you know what? Let's use patterns as case labels in a switch, so that I can ask the question once. Does the argument match integer? If so, do some integer-specific thing. Does it match byte? If so, do some byte-specific thing. And this is already a lot less ugly than the code on the previous slide, but we can combine this with expression switches that we saw a few minutes ago and end up with this. And this is just the facts. This is exactly what you had in mind when you sat down to write this method, which is if it's an integer, do this integer thing. If it's a byte, do this byte thing, and no extraneous ceremony. So that's nice. Having type patterns as case labels is nice. But like I said, we can go a lot deeper than this. And let me just show you one example of where the rabbit hole leads. So we talked about records. One of the things about records is I am a carrier for my data. And we can derive how to make a record, how to take a record apart, how to compare records from that statement of I am just XY. So one of the things that we can derive is how to use patterns to take apart a record. So for example, what I have in yellow here, this is a deconstruction pattern. Never mind where it came from. There's some details about where it came from. Records would get them for free. But the meaning of that deconstruction pattern of are you a circle? If you are a circle, cast to circle, and then call the accessor for the center and the accessor for radius, take those values, and bind those to those new variables, which happen to have been described with type inference, but I could have said point center int radius just as well. Now this isn't magic. I'm not scraping fields. There's some actual science to how this is done. But it allows me to say exactly what I mean. If it's a circle, get the components of the circle that I care about, and now I can operate them in the body of the if. And I can combine this with the switch statement before, and putting it all together. Let's say I'm computing the area of a shape. I know I have a shape. So is it a circle? If so, extract the interesting components of the circle and compute pi r squared. Is it a rectangle? If so, extract the points, compute delta y times delta x. Is it anything else? No, it can't be anything else. It's a sealed type. I already told you that. So the compiler doesn't need to make you put a default clause in because it knows that you have covered all the possible shapes. So these are 3 features that work really nicely together. A way of describing a class that's a carrier for its data, a way of describing a discriminated union so that you can switch over it exhaustively, and a way of taking apart something that you know is a carrier for data. Now, you'll obviously be able to do this with arbitrary classes, not just with records, but it'll be easier with records because you get that all for free since the compiler knows how to generate it. So this is a pretty nice story that will play out over the next couple of versions. And there's lots more in the pipeline from Project Amber. There's more in the pipeline from other projects as well, which I could, like I said, talk about each of these for hours, but I won't. But I think I have like 4 minutes left with which I can take questions. And I saw there were a bunch of questions. This gentleman had a question, and then Ken. Mm-hmm. Yeah. Yeah, so the question is, well, why not just do tuples? Which is basically isomorphic to the question in lambdas of why not do structural function types instead of nominal function types? And the answer is we could do tuples, but now we would have a type system where some types are structural and some types are nominal, and there's an impedance mismatch where the nominal world meets the structural world. And so because people are used to thinking in terms of classes and members of classes, it makes more sense for Java to express data aggregates nominally. One of the things that you get out of them is you get names. A point is called a point. It's not just a tuple of int and int. And it has a type state. It's a point. It's not a range, which is also a tuple of int and int. And its components have names, x and y, versus a range, its components might be lower and upper. So it's more descriptive for a little bit more work, but it fits better into the Java philosophy. Ken? They are, you cannot make them mutable. They are immutable. The field, when you say a point is int x, int y, that's final int x, final int y. But do they still have setters? No setters. Right. Yeah. More questions. Here. So the question is, will I be able to deconstruct something that isn't a record? And the answer is yes, absolutely. But you might be able to do it first for records and then 6 months later for arbitrary classes. We can derive a deconstructor mechanically from the declaration of a record. For a class, you would actually have to declare a member that is like a constructor that runs backwards. So in a constructor, it takes state arguments and balls them up into an aggregate. A deconstruction pattern takes an aggregate and extracts out the pieces. So there will be a way to declare it. It will almost certainly look like a backwards constructor. X equals this dot x, y equals this dot y. But it may be the case that records get them first and then explicit ones come later. So the question is, does it have to, would an explicit deconstructor have to match the signature of a constructor? No. Just like I could have 7 constructors with different signatures in my class, I could have 7 deconstruction patterns, and those signatures might not have to match any constructor, but you probably would want to make it match the constructor because then they compose. Then you can say, take this thing, take it apart, get its pieces, do something with the pieces, feed that back to a constructor, and be able to reason about the result of that operation. So you don't have to, but you'd probably want to. Question in the back, sir. Is there a way to know if a third-party library? Yes, you will find out by running it without enable preview, and it won't run. So you have to explicitly opt in to enable preview at both compile time and runtime. What happens is when you compile a feature with preview, it records it in the class file that this class uses preview features. And then when the VM goes to load that class and it sees it uses preview features and it's not running with enable preview, it will throw an exception at class load time. So I'm told time's up, so thank you very much, everybody.